Okay, we got 10 participants. Hopefully everybody has submitted their homework by now. Let's see. We're waiting on like what, 5 people?
All right, Andrew, I made you the host so you can have a primary control over the whiteboard and stuff.
Cool, I saw, thanks. And I see that we're recording.
You know, I a new page now, right?
There is, okay, let's do this.
All right.
Let's make a whiteboard. And the new page is at the bottom. Cool, I know how to use the whiteboard. Solid. Okay, so excuse me, just a few announcements before we start. First announcement's just going to be about homework. It's the same thing. We noticed that there were a lot of incoming messages, like an hour, 15 minutes, 30 minutes before the homework deadline. And while we are stoked that you guys are doing the homework, we are not so stoked that you're waiting until the last second to do the homework, since we're seeing that, you know, we saw submissions that were all pretty much late. So we have office hours like on the weekends for that reason. Like Alvin sat in a meet for like about an hour and a half, 2 hours, just waiting for people to come, and apparently nobody came. Come on, guys. We got that for a reason. It's for you guys to ask those questions. Seriously, message us on Discord, come there, like just give us time before the deadline to do it. Because if you come to us before the deadline, not only can we answer your questions, we can answer more of them in more detail. Our answers sort of become yes or no questions at that point, because we can't really go through anything with you because the homework is due in like an hour. We understand, like, really, you guys have stuff to do. It's packed, but like, we can negotiate a different office hours time if it doesn't work for a lot of people. But please come to us with that stuff, because we really just need time for that. Alvin, do you want to say the second thing, or should I say the second thing?
Is the second thing regarding chat?
Yes.
Right, so I made it so that now you guys can only chat with the host, because we noticed that things were getting a little bit out of hand. So yeah, that's all.
Like, we understand that like this isn't an actual class per se, so like we're not really teachers, we're not grading like assignments per se, we're not giving you a grade on your transcript, but nevertheless, if you chose to like participate in this team, let's learn. And if we spend too much time chatting, and if we waste a lot of time doing God knows what on the chat, we are not going to have a fun time in the class, because then we have to keep stopping to make sure that you guys are not like doing random things in the chat. We saw people were changing names, sending questionable messages. All right, Our fix for now is just to make sure you can only send messages to the host. So at this point, I will be the only person receiving messages from you guys. And we'll keep it that way for now, just to make sure that nothing bad happens. Okay. So that being said, we can start with our class today. So today's lecture will be on forces and Newton's laws of motion. So let's start. So forces and Newton. So the first big question, when understanding like this basic aspect of mechanics, is understanding what a force is. So can somebody like answer this question? What is a force? So raise your hands, yell it out, write it on the whiteboard, whatever. What is a force? Any takers? Okay, so I got a private message, a vector of motion in a specific direction. Kind of. Well, let's consider this. We have a block sitting on the ground. Are forces acting on this block? Okay, another message, an interaction that makes something move. Okay, so I see in the chat, yes, forces are acting on this block. Is this block moving? No, it's not moving. So it's not per se a vector of motion, because in order for something to have a force act upon it, it doesn't necessarily need to move. So fundamentally speaking, can somebody just like, you guys are thinking in very mathematical terms, and I get it, you know, this is physics. It's got to be something very technical. Just very, very broadly speaking, what is a force? Okay, so I see power, a vector. Okay, so I see the word push. Cool. So a force can be a push. Yeah, there's the answer I'm looking for. It's a push or a pull. So Stephen has written, a force is a push or a pull. It is that simple. That is all a force does. A force either pushes on something or it pulls on something. That's it. That is what we mean when we say a force is acting on an object. So if we go back to this block, where we see that gravity is acting on the block, the earth is acting on the block, and the block is acting on the earth, what's happening? In terms of our definition of a force, in terms of pushing or pulling, what's happening to the block? Okay, so Ivan writes the block is getting pulled by gravity. Yes, gravity pulls the block down and the floor pushes it up. Okay, so not quite with the second part, but the first part is correct. Yes, so what happens is the earth is going to be pulling the block towards it. And similarly, the block is going to be pulling the earth towards it. And that's why the block, and why doesn't the block move? If two things are pulling at each other, in what case does nothing move? If we have two people pulling on a tug of war, what is the case when nobody moves? The forces cancel each other out. Exactly. The net force is zero. So that's why, even though there are forces acting on both of these objects, neither of them are moving, because the net force is zero. And the net force we will be defining as F net. Like that's our notation for net force. Cool. So we understand fundamentally what a force is. it's fundamentally just a push or a pull. So something is either pulling something towards it or it's pushing something away from it. Cool. So somebody refresh my memory. Did we talk about momentum during the last lecture?
We did not.
Okay, so let's talk about momentum now. Because momentum will be our segue into of what forces are and how to define and derive forces. So you guys have probably heard this term, momentums, like raise your hands if you've heard this term momentum ever. Okay, I see a few raised hands. I see actually one raised hand. So nobody else has heard the term momentum.
I can't raise my hand for some reason.
Oh, okay.
Oh, wait, never mind. I'm blind.
All right, cool. I see people. That's okay. Don't worry. No worries. So, okay, I see a lot of people raising their hands. Cool. So you guys have also probably seen the formula for momentum, which I will write in a different color if I can find where the colors are. Here it is. So we define momentum as P equals mv. Now, is P a vector quantity or a scalar quantity? Should I draw an arrow here or should I leave it like this? Okay, I see Jeremy says it's a vector quantity. Does anybody dispute? Okay, so I see some unanimity. You guys are all saying it's a vector quantity. Okay, does anybody want to venture a guess as to why it's a vector quantity? Exactly, it's a scalar times a vector. Scalar is spelled with an A though. Yes, so a scalar product with a vector always yields a vector. Because we know that velocity is a vector, so therefore this is fundamentally a vector quantity. Momentum is also a vector because conceptually, intuitively speaking, momentum also carries, because velocity carries direction with it, your momentum also carries direction with it, because your momentum is proportional to your mass times the velocity. So your velocity, if you're moving eastward, your momentum is like something eastward. So now let's define the units or the dimensions of momentum. So we define it like this. So these square brackets denote dimension of. So what's the dimension of momentum? Well, it's the dimension of mass times the dimension of velocity. So what's the dimension of mass? Or what's the unit of mass? You guys might be more familiar with the word unit. So what's the unit of mass? Kilograms. Cool. So it's kilograms. And what's the unit of velocity? Meters per second. So together we get kilograms times meters per second. That's our dimension of momentum. So if your momentum is 30, it's going to be 30 kilograms times meters per second. And then you also add your direction. So it's 30 kilograms times meters per second east, for example. There we go. So momentum fundamentally describes an object's motion. Momentum is the way that we describe an object's motion. So you guys have all heard the law of conservation of momentum, right? Like, I don't know, raise your hands, put a yes, type a yes in the chat, whatever, if you guys have heard of the law of conservation of momentum. Okay, so I see some yeses, I see some raised hands. So law of conservation of momentum. It basically says in a closed system, so in a system where nothing is being added, nothing's being removed from the system, the net momentum, so the delta P, is 0. Cool. So that is fundamentally the law of conservation of momentum. In a closed system where nothing is being added, nothing's being taken away from the system, the net momentum is 0. Cool. So now from here, we need to define a force. So if we have a force, if we define a force as a push or a pull, and we define momentum as something that defines an object's motion, how can we use momentum to define a force? Or how can we talk about what a force does to an object's momentum? Okay, so Jeremy writes that momentum is to velocity as force is to acceleration. So a force, and Mohammed hits the nail on the head, a force is anything that changes an object's momentum. Cool. So a push or a pull will change an object's momentum. That is fundamentally what a force does. A force will alter in some way, shape, or form an object's momentum. Awesome. Now, if we look at our formula for momentum, P equals mv, what can change in this formula? Okay, so velocity or mass can change. Okay, so that's technically true. Velocity or mass can change. But we're not, the only way for mass can change is if we physically take something from the object or physically add something to the object. Since we're not modifying the object in any way, shape, or form, what could realistically change? If a force acts on something, if a force pushes or pulls, if I push on my computer mouse, am I going to shrink the mouse? Probably not. So what am I changing when I push? The velocity, exactly. So if we talk about it, so this is for a closed system, or here, the sum of the changes is 0 here. We can define then a force as the change in momentum with respect to the change in time. So there are two ways to do this. Way one is to do it algebraically. So algebraically, it's going to be what? M delta V over delta T. Since mass doesn't change with respect to time, it's going to be M times delta V over delta T. And what's delta V over delta T? Well, delta V over delta T is our acceleration, so ma. So we get our famous F equals ma. Method 2 is to notice, oh, look at that. We're defining two different changes. So delta P over delta T, if we decrease delta T and we look at it over intervals and smaller intervals, it'll basically just become dP over dt. It'll be the time derivative of momentum. The instantaneous force on an object is going to be dP over dt. So it's going to be d of mv over dt. And since, again, mass does not change with respect to time, usually, it's going to be m dv over dt, which, again, we define as acceleration. So, again, we get F equals ma. Awesome. So there we go. We see that the force acting on an object is directly proportional to its mass and its acceleration. And that makes sense. You know, what happens when we apply a constant force to something? When we apply constant force to something, it starts to move. And if it starts to move, its velocity changes. If its velocity changes, we now apply a new acceleration to it. Where the original acceleration was 0, our new acceleration is now some other value. It's either positive or negative, depending on which direction we're accelerating. Now, most of you may know this as Newton's second law. So what happened to Newton's first law? So we kind of glossed over Newton's first law with this law of conservation of momentum, with this law of what we'll call inertia. Because again, inertia, you guys have also probably heard the term inertia. Inertia describes an object's resistance to change, which is proportional to its mass and its velocity. Because those are the quantities that will be unique to an object, which is why it is harder to push something bigger to move. Like, for example, if I drop an object, if I drop a book onto the earth, technically speaking, the book is also acting on the earth. So the earth should be moving towards the book. But whenever I drop something onto the table, I don't see the earth moving up to meet it. I just kind of see the thing dropping down to the earth. So that's why we say objects fall. So why don't we see the earth moving up to meet the book? Or I'll put it differently, does the earth move up to meet the book? Yeah, exactly. People are saying a tiny bit. Exactly. It's not a matter of whether or not it moves up to meet. It does. It's just how tiny that distance is. Because if we have a book dropping, it's going to accelerate down at g, 9.8 meters per second squared. Okay, and the mass of the book is tiny compared to the mass of the earth, whereas the earth is massive with respect to the book. And if the earth's mass is so massive, but the force is equal, then that means the acceleration has to be ridiculously small. And I mean ridiculously small. And if the acceleration is that small, then that means that your change in velocity is basically nothing. And if your change in velocity is basically nothing, then your change in position, by extension, is basically nothing. So that's why we don't see the earth moving up to meet the book, even though it technically should be. And it does. So you guys have probably heard Newton's first law stated as an object in motion stays in motion and an object at rest stays at rest unless acted on by an outside force. Well, what do we see here on the board that sort of resembles that law of inertia, that first law of motion? Okay, so an object without velocity has no force, and thus it does not move. Okay, good. So that answers the object at rest stays at rest part. That makes sense. Unless I act on by an outside force, the velocity will stay constant. But what about an object moving? An object that's moving at a constant velocity, if I start moving if this pencil starts moving, like if I start walking, or if I start gliding on like some ice, technically no force is acting on me, and yet I'm still moving. Why am I still moving? Okay, yeah, fine. Gravity is acting on me, but if I were on we're going to assume flat surface. Yes, so nothing is decreasing your velocity, Stephen, exactly. Because why am I moving? Well, no one's stopping me. People, like objects in physics, are what we call inherently lazy. Like, I don't want to stop moving if I'm already moving. It's too much effort for me to stop. It's too much effort for me to start moving. So an object in motion with no outside force on it, with no applied acceleration, if the acceleration is 0, the force applied on it is 0, it will keep moving. And so the momentum will not change. And if the momentum will not change, well, then the net change in momentum is 0. There we go. For a system with 0 acceleration, if A equals 0, then by extension, the change in momentum is 0. Exactly, Stephen. No friction. Yeah, because friction, as we will learn in later lessons, is a force of sorts where the object, the surface on which the object is gliding on, acts against the object's motion. So if I slide a book on the table, why does it stop? It doesn't stop because of gravity, because gravity acts down and the book is moving this way. It stops because the table acts against the motion of the book. And the table acting against the motion of the book will slow it down. But why doesn't the book just not move at all? Well, because in the beginning, your force, the force you applied on the book, is greater than the frictional force necessary to keep it from moving. That's why if you push on the book just a little bit, it won't move. If you push on it a lot, it will move. So there's forces. We have one more law, because I think you guys remember that Newton has 3 laws of motion. And this law is a bit more complicated than the other law. So this law, here, let's just say Newton continued. 3rd law. Does anybody want to venture a guess as to how this law goes? English, physics, math? You can speak it out loud. You can say it in the chat. It's preferable that you guys say it out loud, because not only do I not see you guys, I also don't hear you. Every action has an equal and opposite reaction. Same input, output. Great, exactly. So the way it goes is every action has an equal and opposite reaction. Yeah, exactly. Because if the momentum in a system is conserved, if the total momentum of a system is conserved, and I act on something, if I push on something, well, then technically I've just added momentum to the system. Because I've added to the momentum of that book. So if I'm standing here and I push on a book in this direction, well, the book's momentum has increased. But the total momentum of the system of me and the book has not increased. Well, if we see the momentum here increasing, but the total momentum is not increasing, then what happened? Anybody have an answer? Or a guess? Gravity inputted enough force to cause momentum to go back to 0. Okay. Well, if you notice in this system, it's just me and the book. The Earth is not in this system. If the Earth is not in this system, there's no gravity in the system either. Because Newton's 3rd law will hold in space, where gravity attracts you from all directions. So the answer is that doesn't involve gravity, because again, this system only involves me and the book, and still the net momentum hasn't changed. So it has to do something with me and the book. Okay, good. Jeremy writes, the book pushes me. I'm pushed back. Yes. Mohammed, Jeremy, you guys are correct. Yes, I'm pushed back by the book, because the only way for the book's momentum to increase and the total momentum to not increase is if my momentum decreases. If my momentum decreases, what does that mean? That means it's just increased in the other direction. That means that I was pushed back in the opposite direction. I pushed on this book and I got pushed back. It's the same way as if you sit in a rolling chair and you throw a book or a ball, you're going to notice that your chair slides back a little. Well, why does it slide back a little? Because the thing pushes on you. And now we understand that conceptually, but we still haven't determined this mathematically. We can prove this mathematically. So if we have two systems, if we have two objects in the system, object 1 and object 2, then we describe the two forces, force 1, or force imparted by object 1, and the force imparted by object 2. Well, the force imparted by object 1 plus the force imparted by object 2 is just going to be, you know, the net instantaneous change in momentum of the first object and the net instantaneous change of the second object. So dp1 over dt plus dp2 over dt. Okay, now we know that it's just going to be the change in, you know, p1 plus p2 over dt, otherwise known as the change in the total momentum over dt. And what have we determined? We determined that in a system, the net momentum never changes. In a closed system, the net momentum is always 0, which means this is 0. And if F1 plus F2, oh, forgive me for that little thing. If F1 plus F2 equals 0, then what does that imply? F1 equals negative F2. And if we're talking about the absolute action, the absolute quantity, then we could write the magnitude of F1 equals the magnitude of F2. So, exactly, Andrew. Yeah, they're either both 0 or they're both opposites. So considering they're not 0, considering we push on something, that means that the force at which they push back is 0. Great, awesome. Which is what we call Newton's third law pairs. Every single system, will, wherever there is a force, will always come in pairs. I push on the Earth as much as the Earth pushes on me. But because the Earth is so much bigger than me, you won't notice the Earth following me around wherever I go. So using that, and using the example of the Earth, why is it that when I throw a basketball, I don't shoot backwards at the same speed as the basketball? Why do I barely move? I have a significantly higher mass. Exactly. Because a basketball weighs about, I don't know, 1 to 2 kilos, and I weigh 67 kilos. So which one is going to impart the larger acceleration? Well, the one with a mass of 2 kilos is going to have a much greater acceleration. Yeah, the basketball. And my acceleration by extension will be much smaller. But you do notice that when you throw a basketball, you do move backwards a little. It's precisely because the acceleration is not 0. And because you're not many millions of times more massive than the basketball, you will still feel that change a little bit. Okay, so final question on Newton's third law. So we've just established that every action has an equal and opposite reaction, so all forces come in pairs. So then why is it possible for me to move? Let me illustrate this in a diagram. So if I'm moving on the Earth, right, and I'm walking, and I impart a step on the Earth, I step down, I'm applying an action, and the Earth should be applying an equal and opposite reaction up against me. So why am I able to move places? Because according to this, I should never be able to move anywhere. Because if my foot imparts something, if my foot imparts a force on the Earth, and the Earth imparts an equal force back on me, then I'm not supposed to be, I shouldn't be able to move anywhere. Okay, Jeremy has an answer that is correct. I want to see if anybody else can venture an answer. So let me illustrate this diagram a bit clearer. So we've got a foot here. So I'm stepping down, and the Earth should be going directly up, and I shouldn't be moving. Okay, so Mohammed, so Mohammed said that the Earth's force isn't directly up because it's rotating. Yes, the Earth is rotating, but the force will still be up in all directions because the Eiffel Tower will stand over there, and the Tower of London will stand over here, and the forces is still down towards the center. The force will always be directed towards the center of the Earth. So even if the Earth is rotating, that force vector will also just rotate with the Earth. So not quite that. So Jeremy already has the right answer. Anybody else want to venture a guess? I'll give about 30 seconds to think about it. I'll give you about 10 more seconds. Raise your hands, scream it out, write it in the chat, whatever guesses you have as to why I'm able to move. Nothing? Cool. Okay, so Jeremy, you wanna, okay, so Tracy writes kinetic energy. Well, kinetic energy, kinetic energy doesn't quite describe forces. So kinetic energy describes the energy of motion, right? So if I throw an object, its kinetic energy will be 1/2 mv squared. It'll be proportional to that. That's not exactly proportional to a force, because a force is proportional to your acceleration, which is dv over dt, and your kinetic energy is not proportional to the derivative of velocity. It's proportional to only the velocity. So I see somebody drew something on the board. Okay.
The force, I mean, like the force isn't, I mean, like you're not applying force straight down, right? You're also applying it the other way.
Exactly. So the answer to the question, how can I walk, is, Andrew, you idiot, your diagram is wrong. Because how do you step? Do you step directly down, or do you step at an angle? You step at an angle. Like if I walk, my foot is going to be applied at an angle down. My heel will touch the ground, then I'll kick off from the other leg, and I kick off from the ball of my foot. So the diagram that I drew here is wrong. The diagram should really look like this. That's how I'm walking. So I'm going to be applying a force down this way. And when my foot leaves, and my foot will leave the ground at this angle, from which the earth will impart an equal and opposite force the other way and will push me forward. Because yes, if I stomp like this, I'm not going to move anywhere. But if I step at an angle and I kick off in this direction, the force will be applied this way and I'll kick off. So even though my action will have an equal and opposite reaction, because my reaction is going to be in this direction, then I'm going to move in that direction. Because my action was down this way, my reaction will be this way, and I'm going to move. So that's why I'm able to walk. So I'm glad we got that sorted out. So now we should talk about applications of this and understanding, you know, how we can work with these forces. Well, does anybody want to tell me what step one in solving a physics problem is? Okay, yes, step one is indeed to technically read the question. Yes, so it's read the question, but we're going to call those step 0. We're going to call this step -1, because you're not even solving the problem when you're reading the question. So there's your step -1. Step -1 is to read the question. Step 0 is to identify what you're given and identify what you're solving for. So identify givens and what you want. So now when you actually start solving the problem, what's a good thing to do when you're talking about a problem involving motion? Because it's useful to visualize things. And how can you visualize a physics problem? Yes, I do want you to say draw a diagram. Yes, your next step is to draw a diagram. Now in physics, we call these free body diagrams. So what is a free body diagram? Oh, whoops. Does anybody who's heard of the term free body diagram want to explain what a free body diagram is? Okay, so Jeremy writes crazy scribbles. That is what they devolve into if you draw them incorrectly, or if you have like 8 million things acting on an object. But what is a free body diagram fundamentally? What does it describe? What do you put on the diagram? What does it help you understand? Okay, so a free body diagram simply describes and allows you to understand applied forces, applied moments, and resulting reactions on a body or on several bodies, given some sort of conditions. So for example, so in a free body diagram, you draw vectors that depict your forces. So you have forces acting in specific directions with specific quantities and specific names. So let's draw a very simple free body diagram, like a very simple one. So the first example is going to be just a box sitting on a table. And we want to describe the forces acting on that stationary box. Does anybody want to draw that? Or do you guys want to walk me through drawing it? This would be a good opportunity for you guys to unmute yourselves and speak it out loud. Unless y'all just want to take the board and draw it, which is also fine. Okay, cool. We've drawn the objects. We've drawn a depiction of the table, and we've drawn a depiction of the box. So traditionally, the way you guys drew the object is perfect. It's just a box. Because again, in physics, we deal with what's called point particles. So a person like this, it's very annoying to draw them on a diagram. So we're just going to depict them with either just a single point or a box. That is a human. This is a human. Because to physics, a human is a box. So yes, that's correct. The table, a little bit, you got to be a little bit careful, because sometimes that could be misinterpreted for some sort of pole, some sort of hinge, or some sort of object. So the way you depict that this is indeed ground is by adding these little diagonal lines. So if you ever see something like this, you know that that is a surface. It's a flat surface. So that's basically your key for what something is. So if you see an object, it's an object. If you see this, it's a surface. Yes, you can draw the legs of the table, but because they're sort of irrelevant to our current discussion, because we're really talking about like the simple setup of the surface of the table and the box, that's all that's relevant to our drawing. Because if we were talking about, if we wanted to discuss like how pushing an object would affect the moment of inertia of like the legs of the table, yes, then you have to draw the legs. Or if we start talking about, trying to flip the table over, if you want to flip the table over, you need to draw the entirety of the table, including the legs. But if we're talking about just a stationary box sitting on a table, we can literally just ignore everything except for the surface. Okay, cool. We've drawn the objects, and now we draw the forces. So physics also says that for an object with equal density everywhere, we can essentially just say that the force is coming from the center of mass of the object. And because we picked a very nice shape, a square, the center of mass for a uniformly dense square will be in the center. So this is our central point, or I will draw our central point black because everything else is black in our image. So now, this is where we start drawing the forces. So does anybody want to draw the forces, or do you guys just want to tell me what the forces are? So first, how many forces are there on the object actually, before we write anything or draw anything? How many forces are going to be on the object? Number of forces. Okay, so Mohammed writes 4. Jeremy writes none. We are not pushing the box, Mohammed. No, the box is just standing still. Okay, assuming no gravity. Well, Jeremy, we can't assume that there's no gravity because we now have a reference frame of a flat surface. If we have a flat surface and we know that the object is sitting on the surface, it can be assumed that there is gravity. But even if there wasn't, we still know that the table itself will be exerting a force on the box, and the box will be exerting a force on the table. So yes, so Jeremy and Mohammed write 2. What are they? I kind of sort of gave it away, but if anybody wants to list out those forces, please be my guest. Okay, gravity and Earth. Well, what exerts gravity? The Earth does. So that's one of the forces, yes. So gravity will be exerted down, right, towards the center. Exactly. Beautiful. I saw somebody draw an arrow. Let me erase mine. There we go. That's our force of gravity, which we denote Fg, force of gravity. And what is our other force? Exactly. It's the force that the book exerts on the table. Now, technically speaking, the force should go from here, from the center of mass of the table. But what do we know about vectors and what we can do with vectors in space? We learned about this about, what, 2 weeks ago, 3 weeks ago? What can we do with vectors? We can add and subtract, good. A little bit more geometrically, physically speaking, what can we do with vectors? They can move them around. Yeah, we can move them around. Now, in physics, the best way to like understand reference frames and to work with forces is if all of them come from the same point. So we can move this force vector up here and essentially say that this is where the force is acting. And this allows us to do operations on it, because if the force isn't coming from here, if the force isn't acting from here, it has nothing to do with this force, and thus we can't do anything. Because, for example, if we have some sort of incline right here with another box here, and its force of gravity is and its force is acting, I don't know, for example, somewhere here, this thing has nothing to do with this force because they're acting on different objects from different locations. So it's best, if you're dealing with forces that act on the same object, to have them come from the same object. Now, does anybody know what we call this force? The normal force, yes, Fn. The normal force is always perpendicular to the surface of an object, or the perpendicular to the surface on which the object is sitting. So this is important to understand. If I have an object sitting on an incline, in which direction is its normal force? So this is your incline. Which direction? Does somebody want to draw the normal force from this box? The normal force. So the force perpendicular to the surface that goes out. Perfect, exactly. Now, does somebody want to draw the force of gravity? If we assume that, you know, this is like on the planet Earth. Exactly, straight down, because the force of gravity always goes straight down to the center of the Earth, but the normal force acts perpendicular. Good. And actually, on this, what other force can we say exists on this object on an incline? Exactly. It slides down this surface unless there's enough friction. It slides down this incline precisely because the forces don't cancel out. Because this force vector is also proportional to the cosine of the angle, or the vertical component, the whole horizontal component. They're proportional to the cosine sine of the angle. And because the forces don't directly cancel each other out, there will be sliding unless there is friction. So if I tell you that this object is sitting still on this incline, what can you tell me? There is friction. Exactly. There's a frictional force. And the forces cancel out. Exactly. The net force is 0. And because the normal force isn't enough to keep the object from sliding, there must be friction. And in which direction does the friction act? Top left. Exactly. In other words, against the direction of potential motion. Because if this object starts sliding, it's going to be sliding down this incline. And so friction acts against that potential motion. Perfect. Now, if I say, oh, wait a minute, shouldn't there also be a force here because this object could potentially be moving this way? Am I right in that assessment? Should there be a force down? No. Why not? Okay, so Ivan says it's because it's the result of all those forces. Yeah, that's one way of putting it. Basically, that describes the object's motion. You know, the object will be moving that way, but nothing's pushing on it that way. Nothing's pulling on it that way. There's no, yeah, exactly. The net force may be in this direction. The net motion may be in this direction, but there's no force physically pushing it that way. So hence, saying that there's a force here is wrong. There's no force there. Because the object, again, just because an object is moving in some direction, that doesn't mean there's a force acting in that direction. Or that doesn't mean there's an individual force acting in that direction. We can say that the net force acts in that direction, not necessarily any individual force per se. And I really pray to God that nobody's in the waiting room. Okay, cool.
I've disabled the waiting room because
of
I don't think
last week's fiesta. Wait, so it's weird. Arib hasn't joined. Alvin, you wanna text Arib on the channel because he apparently was asking.
I think Arib said he can't come. So.
Oh, cool. Oh, that's weird. Oh yeah, he says he can't come today.
Okay, just don't worry about it. Keep going.
Got it. Okay, so let's see. We have about 5 minutes until we should take a break. So we kind of understand what friction is. We kind of understand what gravity is. So let's talk about like one other type of force, and then I will briefly mention, and yeah, let's talk about one type of force, and then after we come back, I'm gonna mention the applications of this in problem solving, and then we'll work on some problems. So let's go to one last page. What happens if I suspend a string with if I suspend an object on a string? So I have an object that's weighing down the string and I release it. What happens? So like I'll try to illustrate it with this. This is kind of sort of the best I've got. So if I suspend an object on a string, what happens to the string, or what happens to the object? Mohammed, you're getting a little ahead here. So just like, okay, well, before the string breaks, why would it break? So what happens to the string physically if I suspend an object on the string? What'll happen to it? Just again, y'all are thinking too complicatedly. What happens? It stretches. Exactly. The string just stretches. That's all I'm looking for. We're being very simple here. If I suspend an object from a string, the string will stretch out. Now, we know if we examine our, if I also find where my pen went, here it is. If we look at an object suspended on a string, we know that there is a force of gravity. There's a force of gravity acting down on the string, acting down on the object, pulling it down. This is our FG. And we know that there should be a force acting against it, because does this object move if I suspend it from the string? The object doesn't move, right? Which means there needs to be some sort of net force, but there's no normal force here because there's no surface. This object isn't resting on any surface, which means there can be no normal force. So exactly, there's a tension force in the string that points upwards. We call it a tension force because, the string gets very tense. It stretches out. So this is our tension force that we describe as T, or FT. That's our tension force. And the tension force acts along the length of the string. And we assume in an ideal string that it will go through the entire length of the string, and that the string is not elastic, which means that as soon as it reaches its capacity, it'll snap. So in regular strings and like a normal everyday strings, we see that, it'll extend, it'll tighten, then it'll stretch a little bit past capacity, and then it'll snap. In an ideal string, it'll stretch, it'll hit capacity, and then it'll snap. And we know then that if this object is not moving, that the tension of the string is equal to the gravitational force. And, we can start then, if we understand how tension forces work and how tension forces add, we can start examining like weird pulley contraptions where, we say that here's a pulley, here's one pulley, and here's another pulley. And we say that it's suspended, that it's all suspended here. And we say that this is tight. It's stretched tightly, or taut, it's taut. Can you calculate the tension force of the string, for example, I don't know, here? Or can you calculate, the tension force with respect to like a standard tension force here? Like if we call this tension force T, what is this? We can start solving these types of problems. And it's about 5:30 right now. So I've been talking a lot. So let's just review what we've talked about overall. We've mentioned what a force is. A force is a push or pull. A force will fundamentally alter the momentum of an object. And an object's momentum is a quantity that describes its motion, that describes, an object's motion. And a force describes a change in that momentum over time. We know that in a closed system, when nothing's being added or taken away from the system, the net momentum is zero. So an object, and hence an object at motion stays at motion, and an object at rest stays at rest unless acted on by an outside force. So the net change in momentum of an object with zero acceleration is zero. And we know that we've derived that the force exerted on an object is proportional to its mass times its acceleration, F equals ma. And that, coupled with Newton's first law, coupled with law of conservation of momentum, we understand that every action has an equal and opposite reaction, which is Newton's third law. If I push on something, it will push on me back with an equal force. I might not necessarily feel the same force because I might be significantly lighter or significantly heavier than that other object, which again is why we don't see the Earth meet us when we jump up and then come back down, but it's still there. So we went over Newton's three laws, we went over forces, we went over drawing free body diagrams, and we went over different types of forces, which we can talk about: gravity, friction, tension, and normal force. So all of that will now allow us to segue into a way of solving motion problems, which we delightfully call in Harvard physics classes fan clan. But more on that when we come back in about 10-15 minutes. So why don't we come back in 15 minutes, because I've been doing nothing but talking. So come back at 5:45.
Okay. So we defined we define force to be the difference in momentum over the difference in time, right? Where P is equal to mv. We just make them all vectors. All right, so and we sort of what we did earlier, we were able to drag m outside because we assumed that m was a constant, right? But then that poses the question: what if m varies? So we can actually sort of approach this using a derivative, which is what we did for finding velocity and acceleration as the derivative of velocity and position with respect to time, right? So then the instantaneous force is equal to, well, actually, wait, give me a minute. Actually, Andrew, if you could switch to a new page, that would be swell.
Sure, I will gladly be swell.
All right. So then we can define the force, the instantaneous force, as the derivative of momentum with respect to time. And this in turn is equal to d dt of m times v, right? So then in calculus, you're going to learn about a rule of derivatives called the power rule, which I'm gonna quickly run through and prove because you'll learn it in senior or junior year if you're taking calc now. So this basically states that if you have two functions, f and g, multiplied together, and then you're taking, I'm not gonna do that actually.
I think you mean the product rule, right?
Yeah,
Oh.
yeah, product rule. I'm getting my names confused.
Yes, the product rule is the derivative of products, of functions.
Right, so if you have two functions, f of x times g of x multiplied together, and then you take the derivative with respect to x, then this is going to be equal to d over dx f of x times g of x plus d over ddx g of x times f of x. Right, and then so how we can use the product rule here is that if m, so if both m and v vary with respect to time, then we can use the product rule, right? d dt of mv is going to be equal to m dv dt plus v times dm dt. So like dv dt, as we know from before, is this is just equal to the acceleration, right? So then this is where we get our famous f equals ma, right? But then we also have like this part. So where's this part in our normal Newton's second law, right? Well, in the normal case, we usually assume m to be constant. So then dm dt, the change in m with respect to time, actually just becomes 0. So then, if m is constant, then this is 0, and it's equal to 0. However, if it's not, then we just have like this extra term that we have to account for. So this is actually the full statement of Newton's second law, which is v ma plus v dm dt. Now, can anyone give an example of when like mass might change? And you can like DM that to Andrew, and he can read out some responses. Andrew? Wait, okay, so like who can write it on the board? There's like a very famous example. Yeah, that's exactly right. So No, don't erase that. Whoever typed it, I'll put it back. So, yes, keep writing. Rockets, right? So, rockets. So rockets, they burn through fuel really quickly. So the change in mass with respect to time is actually a pretty significant thing. And if scientists were to have ignored it, then we would have terribly underestimated what we need to get into space, and then all of our rockets would just be pulled right back down to Earth, right? So then this term is significant in some cases where mass changes, but for most cases, you probably don't have to worry about it. But just keep this in mind. It's just a cool thing.
And not only that, but not only does this mean that you need a lot of mass as fuel, you also need fuel that can produce an energy output that could also carry the weight of the fuel. Because consider, you're not only pushing up the rocket, you're also pushing the rocket and whatever remaining fuel you have. So that's rocket science, and that's a lot. Force of a Minecraft house sent flying by TNT where some bits are blown up. Yeah, pretty much. Okay, so let's see. Yeah, so we're just gonna make a few quick announcements. Then we're gonna talk a little bit about like friction and some applications of problem solving with forces, and then we're gonna do a few practice problems. So let's move to the next page. So just a few announcements again. Problem set will be posted either today or sometime tomorrow, along with the lecture notes and the recording of this lecture. Office hours will be held over the weekend. So there will be a designated time from 4:30 to 6:30 on Saturday where Alvin and I will be in a Zoom and we will be able to answer any questions you have pertaining to the material we learned or pertaining to the problems on the homework. You can also message us or any of the TAs literally whenever in the Discord, and we can hop onto an impromptu, like extemporaneous voice channel for the homework. All we ask is that it please be done by the deadline. Really, like we're trying to give as many opportunities to ask questions and do the homework as possible. Literally, we're readily available on Discord. There are plenty of TAs on Discord available to help you with some problems. We'll have a literal office hours session from 4 to 6, from 4:30 to 6:30 designated for this. All we ask is please get the homework in by the deadline. We're really trying to give as many opportunities to ask us questions as possible. Please take them so that we don't have a repeat of this week. We don't have like people not coming to office hours and then asking like firing like questions an hour before the deadline. That's all we ask. Okay. And yes, so we're also going to, again, be moving very quickly as well. So that's another incentive to do the problems because we're going to be moving very quickly. I think we're going to have our first practice F equals MA exam probably maybe next week. So I'll probably post an early practice F equals MA, which is like mostly mechanics, and we'll try to do those problems. Yeah, so now let's talk about the forces that we talked about. So the biggest force that we need to understand other than gravity and like in a lot of these force problems is friction. Friction is really, really freaking annoying because, you have to remember, incidences when it exists, when it doesn't. You need to factor in how frictional forces affect things. It's a mess. So friction is the force that opposes like the standard motion of an object. So there are two types of friction. So can somebody tell me the two different types of friction? There's one and then there's another. Okay, so one of them is static friction and the other is kinetic friction. Exactly. So what does static friction, how can we describe static friction? Like what type of friction is it? Like what does it do as a force? What does static friction do? Okay, so force needed to overcome to get the thing moving. So yes, static friction is friction that opposes motion. So it opposes motion, and it is the force you need to overcome to move object, to move stationary object. And so kinetic friction then is yes, it experiences as it moves. So kinetic friction is it okay, here, let me rephrase. This opposes starting motion. And kinetic friction opposes your current motion. So it is the force that you need to overcome to keep the object moving. So you need to overcome to keep moving object. I apologize if my handwriting is getting a little sloppy. So yes, let's describe two different types of, let's go through a few examples. There is a heavy crate on the floor that I am trying to move. What type of friction is it undergoing? I'm struggling to push a very heavy crate. Static friction. Yes, that is static friction because the crate is stationary and I'm trying to move it. And I'm struggling to get it to start moving. Okay, here's another example. I'm sliding, a book is sliding on a table, but it's slowing down. Kinetic. Brilliant. So we get the very basic types of friction. So we get, a book is sliding on a table, it's moving. Its center of mass is moving. The point of contact is moving, so it experiences kinetic friction, and it's opposing the motion. And static friction, yes, I need to overcome it. Here's a bit of a tricky one. A car tire skidding on the floor. So we have the car moving, the wheels rotating. What type of friction is the thing experiencing? So if I have a car tire rotating on a road, so normally speaking, a rotating body without friction should not be moving anywhere. But because there is friction, it allows it to push off and keep moving. So what type of friction is it? Is it static or is it kinetic? Jeremy, is that your answer to the previous question or this one? Sure. So you have a tire, in a car, the wheel is rotating, right? And so because in order for the car to move, there needs to be some sort of friction between the tire and the ground, because otherwise that's the only thing that allows the car to push off and move, right? So that means that there is some friction between the tire and between the ground. So what type of friction is it? Is it static friction or is it kinetic friction? Okay, so Jeremy thinks it's kinetic, Ivan thinks it's static, Wanjong thinks it's both. So exactly one of you is correct. What do you mean, Jeremy? So the last question was, what type of friction is between the tire and the road? Static or kinetic? If a car is moving and the wheel is rotating, is it static friction or kinetic friction? I can tell you out of the 3 people that answered my question, exactly one of them is correct. What do you mean skid?
All right, so when the ground actually applies friction to the tire, right? Think about if the tire is moving or not with respect to the ground, and then that sort of answers the question or should help.
So I'll give about 1 more minute, and then I'll explain, because this is a weird one. And as soon as you understand this one, all of statics makes a lot more sense. Statics is just clarification, the study of stationary systems. I'm gonna munch on some eggs and bacon while you guys think. Okay, so Jeremy says if it's slipping, then kinetic, otherwise it's static. Tracy says it's static. Wanjang says it's static. Richard says it's kinetic. Okay, so I'm going to reveal which one who is correct. The answer is Wanjang is correct because it depends on the system. So Jeremy and Wanjang, you guys are both correct. So let's consider what happens with a tire. Because friction is a contact force, right? Friction acts between the points of contact. So if we have a book sliding, we have this is our contact area of the book. So when it's sliding, it's moving, all of these points are moving. And since all of the points are moving, the friction opposes the motion of those contact points. And because it's opposing moving contact points, it's kinetic friction. Now, if we have the big box that I'm trying to move, it's stationary, which means the friction that's acting against my pushing force is acting on stationary contact points. They're not moving. And that makes it static. So let's look at a tire. And a tire is a rotating system. That is a terrible circle, but I'll go with it. So what is the contact point? If this is the road, what is the contact point? How can we describe the contact point or points of the tire? The very bottom of the tire, exactly. So this point. And the problem is, exactly, Andrew, the contact points are changing when the tire is rotating. So if the tire is not sliding, if the tire is not locked, the tire is rotating, so that the contact points keep changing, which means the frictional force acting at any specific moment against the car's motion is acting on a stationary contact point or a stationary set of contact points. And because it's acting on a stationary set of points, the friction there is static. But if we take Jeremy's example, if we suddenly brake, like if you're driving a car and you brake and the tires lock and you start hearing that skidding noise, the contact points will remain the same because the wheel is no longer turning, which means the contact points will stay the same. And because the car is moving and the contact points aren't changing, the contact points are also going to be skidding in that direction. And because the contact points are now skidding and the static and the friction force is acting against those moving contact points, the friction there becomes kinetic. Does everyone understand what I just said? If somebody does not understand, please raise your hand, let me know, and I will explain it again gladly. It is very important that you understand this principle. So Wanjang has raised his hand. Yes, so what's wrong? Feel free to say it out loud if you want to, or type in the chat. Why are the bottom points static when moving? Okay, so let's erase what I just drew, and let's look at it just frame by frame, right? So we have our object. The net motion of this car, of this wheel, of everything is going to be, you know, in this direction, right? And the car is going to be rotating in the wheel, the tire is going to be rotating in this direction, which means that at one given point, the contact point is here, right? Pressing against this point. In the next instance, this contact point will be here. In the third instance, this contact point will be here. So the problem is, at any given instant, the contact points are not moving. The wheel is moving, and so the contact point itself changes. It's not, we're not examining a single contact point. We're examining an infinite set of contact points. So this contact point will map to here. Then in the next instant, this contact point will map to here. In the third instant, this contact point will map to here. So in total, the object will be moving in this direction, but the given contact points of the wheel will always be stationary at every given instant. So the reason the tire moves is not because the contact point itself moves, or because the contact point moves as the wheel moves, but because the contact point changes. And so we look at different contact points. So the friction is always going to be acting against that contact point at that given instant, but that contact point at that instant is not going to be moving. So the friction is going to be acting against stationary contact points. It just so happens that those contact points are always changing. And so the friction between the tire and the ground will still be static. So what about the contact points on the ground? They don't matter. Well, consider the ground isn't moving, right? So the contact point is always going to be stationary with respect to the ground, right? So the ground is not moving anywhere. It's the same as if I slide a book on the table. The table itself isn't moving. The contact points with the contact points of the book with the table will move, but the contact points on the table will just change. So if I look from here, for example, you know, the contact points at this part, you know, the book, it'll be the same contact points. It'll be these contact points. And on the table, it'll be these contact points, right? But as the book moves, here, the contact points of the book will remain the same, but the contact points on the ground will change. So the contact points on the table or the ground are, for all intents and purposes, stationary. They just change from frame to frame. The same thing with the tire rotating on the ground. The contact points are going to be changing for both the tire and the ground. So they're both static, and they're basically just both rubbing against each other for an instant. So here, then here, then here, then here, then here. So if you pause at every single frame, the contact points will be different. And so for that instant that that contact point is touching the ground, it is stationary. So the friction is acting against a stationary contact point. And so the friction is static. Does that make sense? Like thumbs up, or I don't know, a Y in the chat if it makes sense, kind of ish. Not entirely. Okay, so
I mean, I guess we're gonna be revisiting this when we talk about rolling, the dynamics of rolling, right? Circular dynamics.
yeah.
So I guess this is called like rolling friction, by the way. So we're going to be revisiting this. So don't worry too much about it for now. Because once you understand like how rolling works, then this might be a lot more clear. But just for now, just worry about like the book sliding across the table instead of the wheel. All right. We're gonna push
Just accept it.
the proof, I guess, for this for later.
Yeah. So, okay. I'm glad it kind of makes a little bit of sense, but yeah, it'll definitely make a lot more sense in the future. And my computer is not charging for some reason, so give me 30 seconds to understand why my computer is not charging. Pardon me. Just give me a few seconds to understand what in God's name is wrong with my computer. Ah. Beautiful. Or not so beautiful. Okay, beautiful. Sorry about that. My computer just decided to be weird for an instant there, but now it is back. Kind of. Yeah, whatever. I'll worry about it later. Okay, just for now, I'm glad you guys sort of understand what's going on. Don't worry, it'll make a lot more sense in the future. Really. So for now, we're just going to be dealing with like stationary, excuse me, with stationary elements. Yeah, okay. My display is being odd. Okay, I'll figure this out later. My bad. Okay, so we're going to be worrying about just regular friction for now. So static kinetic, it's all just basic for now. So I hope that makes a kind of sort of sense. Okay, beautiful. I just fixed a weird issue I've been having with my computer. Okay, cool. Yeah, that's friction in a nutshell. So in a nutshell. It acts to prevent motion, or it acts to slow down existing motion, which again, if we return to our incline problem, we get the same thing. Where if our object is stationary, static friction will act against it while the object is stationary. So how is it possible for objects to move if the static friction is really a thing that could happen? How is it that objects ever move if static friction can pose an issue? My chat disappeared. So until I can find my chat box, I'm a little lost. Huh. I'm gonna stop the share for a second. I hope it saves so that I can find the chat. Okay, there we go. Cool. So gravitational force exceeds the static force. I see you guys wrote that. For some reason, I still don't see the chat, which I think is weird. What's this? Okay, my apologies that this has been taking so long, but yes. So my chat is gone, so I'm kind of going blind. So I'm going to just speak, and if you guys have an issue, raise your hands so that I can see you.
I mean, I guess something you can do is just change the chat back to public.
Yes. Okay. So I will change the chat back to public on one condition, guys. Please limit the randomness of the chat. Really. We've had a lot of like issues with people like in complaints about people feeling uncomfortable during the chats. Let's keep it to that. So Participant can chat with everyone publicly. Nobody can chat with anyone privately. Let's put it like that. Okay, I have changed the chat settings. Hopefully y'all can see them now. Okay, now I'm going to go back to the share. I don't know what happened there, but Alvin, yes, please be my chat reader so that I can see what people are saying until that gets resolved. Okay, so yes. In order for this object to start sliding or to start falling, the gravitational force or the net force in this general direction needs to exceed this static force. So if I start pushing on an object, this static friction, F, or we usually say little f to denote friction, Fs, static friction, as soon as the applied force Fa is greater than our static friction force, the object starts moving and we start working with kinetic friction. So static friction, you guys may have seen the formula for static friction, but it's going to be something called mu s Fn. So it's proportional to the normal force times what's called the coefficient of static friction. So every single object or every single surface has a different coefficient of static friction. And usually, if you're asked to calculate the frictional force, you're going to be given the coefficient of static friction with that surface. And similarly, the kinetic friction force is equal to mu k Fn. So again, if we look here, the static friction force is going to be proportional to this normal force times the coefficient of static friction. And here, it's going to be proportional to this normal force times the coefficient of static friction. Which is why, if I have a wooden incline and a wooden surface, what could happen is the friction force, how could we describe the friction force with respect to the friction force on the ground here? How is the static friction force going to differ? Is it going to be greater than it? Is it going to be equal to it? Is it going to be less than it? How can we describe that force? Anybody write anything in the chat?
I got nothing. So if the frictional force is directly proportional to the normal force, then if the weight of the object increases, then the normal force is also going to increase in order to match it, right? So then if the normal force increases, then what happens to the amount of static force that's necessary? Anyone? Yeah, so Fs goes up.
And we know that these things are also proportional to the angle between the sine and cosine of the angle. So a nice way to look at what happens to the forces is to consider extreme cases. So let's consider an extreme case. Extreme case number one, the surface is completely horizontal, it's flat. And I sit down an object. Is the object going to move?
All right, so Stephen says no.
Exactly. The object is not going to move. Okay, let's consider another extreme example. It's vertical. I'm trying to put a block against a wall. What's going to happen to the block?
Yeah, it's gonna fall down.
Exactly. Which means that the static frictional force has to, how does it change? It's at its minimum when it's here, and it's at its maximum when it's here, which means that as the angle decreases, what happens to the static frictional force? As the angle like decreases with this surface and the ground, as the angle decreases and it becomes more and more level with the surface, what's going to happen with the static frictional force? No takers?
Someone said F of S increases. 2 people say that.
Yes, exactly. Because it'll go from its minimum value to its maximum value, which means the static frictional force will increase. And if we know that the force increases as the angle decreases, what do we know that it's proportional to with respect to the angle? What trigonometric identity do we know that can relate this? That it decreases or it increases as the angle decreases.
Actually, like this could be proven using angle chasing. So that actually might be a more rigorous way to do it. Would you mind like switching the page?
Sure, yeah, you can do it rigorously. But intuitively speaking, it's going to be based on the cosine of the angle. Because if the force increases as the angle decreases, because we know it'll just fall immediately here, and it won't move at all here, even though the net force downward is the exact same, FG is never going to change. So we know that FS has to be way smaller here than it is here. We know that then it must increase with respect to the angle decreasing, which means that it has to be proportional to the cosine of the angle, because the cosine is 1 here, which means that the frictional force is at its maximum value here, and it's 0 here. So there's basically no friction between the thing and the ground, because regardless of how big the friction is, how heavy the object is, if you try to put it against the wall, is it ever going to stick to the wall? No, it won't, unless the wall itself is sticky. And I'll let Alvin take the angle chasing approach for however long it takes. Let's see, we've got 4 minutes, so let's actually finish on this.
Yeah, okay. So just a clarifying point for the coefficient of friction, this mu, right? So then first of all, between the 2 different types of friction, mu s is typically going to be not equal to mu k. In fact, mu s is going to be typically greater than mu k. So then it takes more to start an object's motion than it is to like overcome the kinetic frictional coefficient. And these coefficients are going to be given, right? It depends on the material of the surfaces that you're working with. So for example, if you're sliding something across sandpaper, then it's going to have really high coefficients because the surfaces are going to provide a lot of friction. However, if you're sliding something across, like for example, ice, then the coefficient is going to be like virtually 0. So these are, and in a normal physics problem, these are going to be given to you. These are values that are going to be given to you. So like the frictional force is equal to mu times the normal force, right? So then I guess we're going to derive like the frictional force. And yeah, the frictional force that's needed to keep this thing in place. So first of all, we know that there's always going to be a gravitational force that's acting down on the object, right? So then regardless of like what angle the incline is pointed up, it's always going to go downwards at mg. And then we know that the force has a magnitude of mg downwards because like F equals to ma. And then since the acceleration is always going to be g, we just know that F is equal to mg downwards. So because of our vector addition laws, we can decompose the vector mg into a component, like we can choose like two axes to make it simpler, right? We can choose our own coordinate system. So which is why I'm going to choose like the downward. I'm going to choose the x-axis to be parallel to the surface of the incline, and I'm going to choose the y-axis to be perpendicular to that. All right, so the x and y axes are always perpendicular to each other. So now we can do a little bit of angle chasing, right? So first of all, we need to find like Fn. So first of all, what is this angle going to be? We can find that by taking this angle, right? This angle, because mg is always perpendicular to the ground, this is going to be 90 minus theta. But then I'm going to label some points here. This is like A, this is B, and this is C. So then since we decompose mg into a component that's perpendicular to the plane and one that is parallel, then we can also say that the angle BCA is equal to 90 degrees. Right, so if this is 90 minus theta, A, B, C, D, if BCA is 90 degrees and DCB is 90 minus theta, then what is the measure of angle ACD? Someone said theta. Ivan, Steven. Yeah, very good. So this is going to be theta. And now we can confidently say that the vector AD has a magnitude of mg sine theta. And also, CA is going to have a magnitude of mg times the cosine of theta. Right, okay, so now since the block is not experiencing any motion whatsoever on the y-axis, then that means the sum by Newton's first law, the sum of the forces on the y-axis is equal to 0, right? Which means we have to make this cancel out. And since the only other force acting on the y-axis is the normal force, then that means, and this is, the mg cosine theta is acting negative, is acting in the negative y direction, right? So then that means negative mg cosine theta plus the normal force is equal to 0, right? And therefore we can use that to determine that the normal force is actually equal to mg cosine of theta. And excuse me, I'm keeping you like a tiny bit over time, but we're just going to be ending on this. So the normal force is equal to mg times the cosine of theta, which is what was said earlier. And it makes intuitive sense because if theta were equal to 0, then the incline would be flat. And the normal force would just be equal to mg, right? But then if it were just a wall, right, then there would be no normal force and the object would just be, kind of falling. Okay, so what about the friction force? So then we were asked to solve for a friction force such that the block doesn't move, right? And then as we see here, the part of the force that is parallel to the incline has a magnitude of mg sine theta, right? So which means that if we want to cancel out the sum of the forces on the x direction, then that means we also need negative f, because that's acting in the negative x direction, plus mg sine theta is equal to 0. And this shows us that f is equal to mg, the magnitude of f is equal to mg times the sine of theta. So, and then since f is equal to mu times the normal force, then this leads to mg sine theta is equal to mu times the mg cosine theta. And here we can actually cancel out mg on both sides. And we get that the mu, in order to make it work, the coefficient of friction on the surface has to actually be equal to sine over cosine, which is equal to tan of theta. So, if you see mu equals tan of theta on an incline, that's like the magical value for which the block is going to stay put on an incline. All right, so that's all I got this week. So the P set is going to be posted like tomorrow, probably. And as usual, it's going to be due on Monday. So is there anything else you want to say, Andrew?
Sure. So just, we didn't really work through like a big problem with regards to forces and everything. But again, we'll probably discuss this during office hours if like a lot of people have a lot of questions regarding this. But when it comes to solving a problem regarding forces or regarding friction, set up your diagram, write out the forces that actually affect your system. And if in statics, we know that the net force will be 0. So if the net force is 0, then that means that the sum of all the forces in your system will be 0. Some of the forces will be known, other forces will be expressed in terms of known quantities, which means from there, you can try to calculate the values of the forces that you don't know, because you know that them plus forces that you know will be 0. That fundamentally is how we solve statics questions. That's what statics is. It's the study of no net change. So on the P set, you're going to see a few problems where you have to, calculate some forces, or you have to like compute something. And what you know is that the system is stationary. Nothing is moving. If nothing is moving, the net force is 0. The net force is 0. All the sums will be 0, which means you can compute the forces from there. Again, if you guys are really having a lot of trouble on this, we will discuss it further in the office hours, but just know. And again, please attend the office hours if you have questions. We really don't want to be cutting it so close with the deadlines anymore. We got to keep moving. And, forces and all this is not a super complicated topic, but as soon as we get to more complicated topics, if y'all like forget things that we did before, it's going to be very hard to catch up. So for your sake and for ours, please, let's do the homework a bit earlier.
All right, that's all. We'll see you all in office hours or next Tuesday.
Yeah, until then. Adios.
Of course, like if you have any questions, you can stick around.
Yeah.
Bye. Okay.
Well, they left quickly.
Okay.
Let's.
You should save the whiteboard.
Yeah. How? No idea. Just what? Save. I saved all the whiteboard, right? Okay.
Yeah. So
And
then,
now how do I?
when you can, post it onto the classroom.
I think you